Hello everyone, I want to welcome you to another section. In this video, I'll be discussing about nuclear magnetic resonance. Basically, or let me say, I will be focusing on proton NMR because that's the major focus for this particular video. What is an NMR, or what is nuclear magnetic resonance? It's also another spectroscopic technique that is used in elucidating the structure of compounds, and it works based on the principle that nucleus of some atom has capacity to absorb radio waves under the influence of an external magnetic field. So when these nuclei absorb these these radio waves, they they move from a low energy state to an high energy state, which makes them to resonate with the external magnetic field because nuclei themselves they have magnetic properties. It is not all nuclei that are NMR active, so we must take note of that. There are some nuclei that are not NMR active, and there are some that are NMR active. To be more specific, nuclei even number even numbered mass number or atomic number are not usually NMR active because they have zero spin number, while nuclei with odd mass number or odd atomic number are usually NMR active. So comparing a nuclei like C12 and C13, carbon 13 will be NMR active because the mass number is odd, while carbon 12 will not be NMR active because the mass number is even. So please take note that not all nuclei are NMR active except for those that have a non-zero spin number. At the same time, nuclei with non-zero spin number are usually having odd number um, mass number or odd atomic number. This set of nuclei are usually NMR active. So another thing I want to talk about is how do you read your NMR spectrum. Just like how we talked about reading higher spectrum, reading mass spectrum, the same thing still applies when we are reading our NMR spectrum. In an NMR spectrum, you have a plot of intensity of a signal against the chemical shift of that particular signal. So the vertical axis of an NMR spectrum shows the intensity of a signal, while the horizontal axis shows the chemical shift of that particular signal. To read an NMR spectrum, there are four basic things that you have to know about an NMR spectrum, which include number one, the number of signals in the NMR spectrum given to you. Number two is the chemical shift of each of those signals that you have in the NMR spectrum. Number three is the multiplicity of those signals that you also have in the NMR spectrum. And the last one is the integration of the signal. Each of these points I'm going to explain one by one and how they help in elucidating the structure of any compound represented by the given NMR spectrum. So to note those 4 points, I talked about the number of what? The number of signal. Number of signal. The number of signals in an NMR spectrum indicates the different kind of hydrogens that are present in the compound represented by the NMR spectrum. So for example, if you have a NMR spectrum with 4 signals, it implies that in the given compound, in the compound represented by the NMR spectrum, there are 4 different kinds of hydrogens in that particular compound. If you have an NMR spectrum with let's say five signals, it implies that there are 5 different kinds of hydrogens in the compound represented by the NMR spectrum. So the implication of the number of signals in an NMR spectrum is to help us to note the different kind of protons that exist within a particular compound that the NMR spectrum represents. That is the essence of the number of signal. The second thing you have to consider is the chemical shift. Like I said, the horizontal axis of the NMR spectrum is indicates the chemical shift. So each of these signals that you have in an NMR spectrum has its own chemical shift. And the implication of chemical shift most times is to tell us about the chemical environment of each of these signals, or let me say the protons generating this set of signals. Like I said, different signals implies different kind of hydrogen. So the chemical environment of each of these signal, or let's say each of these protons, can be known from their chemical shift. So different protons have different value for their chemical shift. For example, the terminal hydrogen of aldehydes usually have a chemical shift of around 9.4 or so. The same thing applies to the protons of aromatic ring system. The proton directly attached to a benzene ring usually have a chemical shift of around 7.29. So different hydrogens in different chemical environments have different chemical shifts. At the same time, chemical shift is guided by some rule. That is, signals with high chemical shift are usually very close to either an highly electronegative element, or they are very close to an electron withdrawing group. That's when you have a signal that has a particular, or let's say protons with high chemical shift. But when you have um, hydrogens or signals that are very far from an highly electronegative system, or probably very close to an electron donating group, such protons, or let me say such signals, usually have low chemical shift. The reason is because the electrons around the nuclei tends to shield the nucleons from the influence of the external magnetic field, and this therefore reduces their chemical shift compared to a nuclei with few or no electrons around them. They try to experience the external magnetic field more, and therefore they have a very high chemical shift. So if you have a proton that is very close to an highly electronegative system, or even an electron withdrawing group, such protons or signals usually have a very a very high chemical shift, while those ones that are far away from they are far from an highly electronegative element tends to have low chemical shift. So like I said, chemical shift help us to know the chemical environment, give us an indication of the chemical environment of different kind of protons that are producing different signals that we have in an NMR spectrum. So and I've given us a few value of chemical shift for some particular protons. For example, I talked about the terminal hydrogen of aldehyde compounds, the chemical shift of hydrogens directly attached to a benzene ring, and others like that, which also have some particular chemical shift value that can always be an indicator of their chemical environment. The third thing which I talked about is multiplicity. Now, the splitting pattern of a signal, which I also refer to as the multiplicity of a signal, only tells us about the number of hydrogens, or let me say indicates the hydrogens in the surrounding of a particular signal. So adjacent carbon to the carbon carrying the hydrogens that are responsible for a particular signal, such adjacent carbon usually carries hydrogen. So we can know the number of hydrogens on all available adjacent carbon surrounding a carbon carrying the hydrogen producing a particular signal. So if you know the number of hydrogen on every adjacent carbon around a particular signal, that can be used to determine the multiplicity. And multiplicity work by a rule which we can term the n plus 1 rule, which implies that if I have 4 hydrogens on the surrounding carbon atom, the multiplicity of that signal will be 5. If I have 3 hydrogens on the adjacent carbon around a signal, so that means the multiplicity will be 4. So multiplicity follows n plus 1 rule, where n is the number of hydrogen on the adjacent carbon to the carbon carrying the hydrogens that are responsible for a particular signal. So in determining multiplicity, you must first of all identify the adjacent carbon to the carbon carrying the hydrogen that are responsible for a particular signal. After you have identified the number of hydrogen on the adjacent carbon, you add 1 to them, and that gives you the idea of the multiplicity. And you can go in the reverse direction where you know the multiplicity and you use the multiplicity to get the number of hydrogens on the adjacent carbon atom to a particular carbon carrying the hydrogens that are responsible for a particular signal. And the last aspect is what we term the integration of the signal. Integration of the signal. Integration of a signal help us to know the number of protons or number of hydrogens that are responsible for a particular signal. You can imagine that you can have 9, there's possibility of having 9 hydrogens producing the same signal at the same time having the same chemical shift. You can also have 6 hydrogens or protons that are in the same chemical environment producing just one signal at the same time having the same chemical shift. So what will help us to know the number of protons that are responsible for a particular signal is the integration of the signal. And usually, integration of a signal is usually indicated by the area under that particular signal. And they can always give you the value of for areas under a particular signal so that you can be able to determine the number of protons that are responsible for a particular signal. So, but please do not mix up the multiplicity with integration of a signal. What the two of them does is certainly different. Integration of a signal tells us about the number of hydrogen that are responsible for a particular signal, but multiplicity gives us an indication of the number of hydrogens on the adjacent carbon to the carbon carrying the hydrogens that are responsible for a particular signal. So they are saying different things and they must not be mixed up while interpreting your NMR spectrum. So these 4 major things are things to always look out for in your NMR spectrum, and they are enough, or let me say adequate, for you to be able to interpret any NMR spectrum given unto you. So in order to give us an idea of how to apply all of these things that I've talked about, I'll be using ethyl ethanoate as an example for us to follow. So I'll be discussing how the NMR spectrum of ethyl ethanoate will look like in this particular video. This is ethyl ethanoate. It has a CH3, the ester functional group, the what's it called now, the CH2 and another CH3. Now, one thing that you must know is that most times hydrogens in the same chemical environment, they are always at the same distance from a particular functional group, which can either be an highly electronegative atom or even can be an electron withdrawing or electron donating group. But in this case now, if you look at this, you can say that this CH3 here is attached to this what, to the carbonyl functional group, which is C double bond O. But this ethyl part is attached to what, to this O. So that implies that this CH3 that we have here and this ethyl group that we have here, they are in different chemical environments. At the same time, these two hydrogens here, the two hydrogens that we have in this box, they are very closer to this oxygen compared to this last CH3. That also implies that these two also will be in different chemical environment based on their distance from the oxygen, which is an highly electronegative element. So, but the first thing I said was that the CH3 we have here and this ethyl functional group, they are attached to different things. This CH3 is attached to carbonyl, while this ethyl is attached to an oxygen. So that already indicates that they are in different chemical environment. But at the same time, the CH2 are is much closer to oxygen compared to this CH3. That also means that they are in what, in different. So that means now, with what I've done now, I could conclude and say that in the NMR spectrum of this ethyl ethanoate, I'm going to have three different signals because there are three different kinds of hydrogens in this compound. So labeling them, I can say I have HA, 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 HB, HB, HC, HC, HC. So in this particular compound now, I'm having three different kinds of hydrogen, which means that the NMR spectrum for this particular compound will produce three different signals. That's what that indicates. So, and that's the major thing I've probably tried to mention about talking about the number of signal. The second thing I talked about is the aspect of chemical shift. Now, you can always read the chemical shift of this. You can read the chemical shift of this. You can read the chemical shift of this. There are tables of values that are used in reading the chemical shift of each of these protons that we have in different chemical environments. So the three signals that will be produced in the NMR spectrum, they will have different chemical shifts. But like I said, there are tables of values that you can always use to read each of these particular hydrogens. For example, in the tables of values, if you want to read for this CH3, you look for a column, you look for the table where you have your CH3 and you have C double bond O and you have O what, OR. So you look for the chemical shift of these particular hydrogens, that is your sp3 hydrogens attached to this particular functional group. At the same time, you want to read for this, you look for where you have CH2 and you have OC double bond O and you have R. So you look for the chemical shift of these two protons, and that's how you get the chemical shift from the table of values. At the same time, for this last one, you have to check for where you have CH3 attached to C and you have OC double bond O and you have R. Because between this functional group, which is OCOR, you have a carbon in between them. That's why you are having this one here. So, and that's how to read the chemical shift of different protons from the table of values given to you. Now, the next thing I talked about is the aspect of multiplicity. So I've talked about the number of signals in the spectrum. I've talked about the chemical shift and using the table of values to get the chemical shift of each of these different protons. The next thing is to talk about the multiplicity. For the multiplicity, like I said, you have to check for the adjacent carbons to the carbon carrying the hydrogen responsible for a signal. Now, we've already known that these three hydrogens are giving us the same signal because they are in the same chemical environment. But in this structure now, there is no adjacent carbon to this carbon. The carbon carrying these three hydrogen, there is no adjacent carbon to it that is carrying an hydrogen, or let's say a proton. So because there is no adjacent carbon with an hydrogen, that means that for this particular set of protons, we are going to have our n will be equals to 0. So when you add 1 to it, so n plus 1 will be equals to 1, and that means that the multiplicity of this set of hydrogens will be 1. and that means the signal will be a singlet. That's what that implies. Now, if you look at for these two protons that are also producing one signal, so to determine the multiplicity of their signal, what I have to do is I have to consider the adjacent carbon to this particular carbon that is carrying the 2Hb. So the only adjacent carbon to this carbon is this one, which is carrying three protons. So the adjacent carbon to this one that we have here, the adjacent carbon to this one. So this one, like I said, is the what? The singlet. The singlet, because the multiplicity is what? Is 1. But for this one that we have here, the adjacent carbon to this carbon carrying the two of them has 3 protons. So that means our n in this case will be equal to 3, and n plus 1 will be equal to 4. So that means this will be a what? A quartet. So the multiplicity of these two Hb will be a quartet, even though they are coming out as a single signal. So the single signal for these two Hb will be a quartet because the adjacent carbon to the carbon carrying the two of them has 3 hydrogens. Now for this last one, which we have here, the 3 hydrogens are also in the same chemical environment, they have the same chemical shape, and they are coming out as a single signal. But the multiplicity of their signal will depend on this one, which is adjacent to what? To the carbon carrying the 3 of them. So, but this adjacent here has just 2 hydrogens. So the n for this one will now be what? The n here will be equal to 2, and that means n plus 1 will be equal to 3. So that means the signal for this 3HC will be what? Will be a what? Will be a triplet. So, and that's what multiplicity does. And like I said earlier, as you can go from this place to get the multiplicity, you can also, when you are given the multiplicity, you can also use it to do a sketch of how a particular or a sketch of the structure of any given compound that your NMR does represent. And the last thing I talked about is the integration of a signal, which I said indicates the number of hydrogens that are responsible for a particular signal. And I said in most cases, they will give you the value of the area under a curve under the signal to be able to get the value for the integration of a signal. So if you do that, for this one, it will be what? It will be 3, value will be 3, this will be 2, and this will be what? Will be 3, because there are 3 hydrogens responding for this single signal that is coming out as a triplet. There are 2 hydrogens responsible for this signal that is coming out as a quartet, that is in terms of its multiplicity. And in this case, there are 3 hydrogens responsible for the signal that's responding for this signal that is coming out as a what? As a singlet. And that's an application of all what I've explained in this particular case. So like I said earlier, the 4 major points which I've mentioned, which is one, the nature, the number, sorry, which is one, the number of signals in an NMR spectrum, which indicate different kind of hydrogens that you have in the compound represented by the NMR spectrum. The second thing is about the chemical shift, which indicates the chemical environment of these different protons that you have in producing signals in the NMR spectrum. And the third thing I talked about is the multiplicity, which indicates the number of hydrogens on the adjacent carbon to the carbon carrying the hydrogens responsible for a particular signal. And the last one I talked about, which helps us to know the number of hydrogens that are certainly responsible for a particular signal. This is just like a short explanation and a brief explanation on how to quickly go through your NMR spectrum to read it and to get what they are trying to say from an NMR spectrum. I hope in the next video I'll be able to probably bring a question to us and solve that particular question in order to for us to have a better understanding of how to read an NMR spectrum. At the same time, in the subsequent video, I will also try to bring an example of a question whereby different spectroscopic techniques that we have talked about, which include the UV, the infrared spectroscopy, the mass spectroscopy, at the same time, the NMR are combined for elucidation of structure or for prediction of structures. and that will also further help our understanding of all what we have learned so far. I want to thank you for staying tuned to this channel and for watching every video that we have been dropping on this channel, and we promise to become more better in trying to produce content that would certainly be of help to you in your academics. And if you have any question about this set of topics that we have been discussing, you can do us to try to drop your questions, your comments and your suggestion in the suggestion box or in the comment section. You can also try to message me on my email or through this particular platform. I will be very happy to respond to your questions, your suggestion and your comments about our videos and content on this particular channel. And please, I also want to implore you to help us share the link to these videos to fellow students or colleagues or people who you know might be in need of this or some of these lessons. And also, don't forget to subscribe to this particular channel. As you are watching our content, which we believe will be of great help to you academically, please do not forget to subscribe to this particular channel. So please, if you have not subscribed, don't forget at the end of this video to click the subscribe button. Thank you.